Hi, and welcome to another edition of Easy Theory. So today we're going to actually have a relatively long video, and we're going to show a lot of languages are not regular. So we've been talking about this thing called the pumping lemma, and what it said was that if a language is regular, then it has certain properties. It has a pumping length, such that if you have a string in the language and the length of that string is at least that constant that exists, then we can assert that there are multiple properties of that string such that we can pump it numerous times. There are three pieces, X, Y, and Z, and we can put extra copies of the middle piece and we still get a string in the language. So what we want to do if we want to show a language is not regular is to assert that it is regular first, and then therefore by this lemma it must have some properties, but then we show that the language in fact does not have those properties. And so it contradicts the fact that the original language was regular. So the proof strategy that we're going to use here to show a language L is not regular is the following. So we're going to first suppose that L is regular. So we start by doing that. So this is what is called a proof by contradiction. I'll even write that down. So this is a proof by contradiction. The thing that we want to prove is exactly the opposite of what we're supposing here. And if by getting a contradiction at a later point, then we will really prove what we set out to prove, because our supposition here was just wrong. So what are we going to do here? Then we know that there exists a pumping constant P for L, because that's what the lemma asserts. If the language is regular, there is a pumping constant. And if you remember, the pumping constant corresponds to the number of states in the DFA. Well, if the language is not regular, then this pumping constant can't possibly exist because there's no DFA for it. All right, so what we need to do is to think about how we're going to actually prove this here. Well, if we think about it, well, the lemma says that we can pump every single string in the language and having length at least p. The lemma asserts we can pump every single one. So if I want to show that that can't possibly happen, all that I need to do is to show one counterexample, one string, such that we can't pump it. Okay, so then what we need to do is to here choose one. You can choose multiple if you wanted to, but we only need to do one. One string W in L. So a lot of students miss this. You have to pick a string in the language because otherwise you can't say anything about it. And the length of W is at least P, where P is this pumping constant from earlier. A lot of students miss this too. If it's not of length at least P, we can't guarantee that there's the loop in the DFA, and therefore we might not be able to pump it anyway. So we wouldn't be able to say anything there. So we need to have both properties here. Okay, well now what do we do there? Well, we want to show that this string can't possibly be pumped. Well, the lemma says that you can find some way of breaking the string into those three pieces, such that you can repeat the middle piece and all that stuff. But I want to show that there's no possible way of doing that, because if I leave one possible way out, then that might be the way in which a DFA could possibly exist. Okay, so what we need to do is to look at every single one, decomposition, if I can spell decomposition, every single one of W into those three pieces, X, Y, and Z, such that the length of Y is at least 1, and the length of X, Y is at most P. If you remember from the proof video, we don't actually need this condition, but it makes it substantially easier. Then, as the final step, what we need to do is to observe what the other condition is. These are two of the conditions. How do we actually approach the third one? Well, the third one says that x, y to the I, z is always in L for every choice of I, meaning that we can pump the y piece as many times as we want. So it says, the lemma says that it's always in the language for every choice of I. But if I want to find a counterexample, I just need to assert one value of I for which it's not in the language. So we need to find one, or you can find more, but again, you only need to find one, I such that x, y to the I, z is not in L. And that would contradict the fact that it's always in the language, meaning that this string W can't possibly be pumped, which means that the for all condition for every single string being pumpable is just not true anymore, which means that L couldn't have been regular to start with. And that's the general proof strategy. Okay, so let's actually get into a proof here. So let's look at the prototypical language, and we'll see this language quite a bit. The language is 0 to the n, 1 to the n, where n is at least 0. And I've actually done the videos on the languages we're going to talk about here. So this isn't a new thing on our channel if you've been a fan of this channel for a while, but it's good to actually go through the proof again. So I want to show that this language is not regular. I haven't proved that yet. I need to be able to prove that to you. So how do I actually go about proving that this language is not regular? Well, our general proof strategy, let's go about doing that. The first step, of course, is to suppose that L is regular. Okay, we're just assuming that it's regular, then there exists that pumping constant P. So there exists a pumping constant P for this language right here. This language right here. So now what we need to do is to pick some string in the language having length at least P. So a lot of students try to pick a string like this. So choose W to be 0 to the P over 2, 1 to the P over 2. Meaning I have a string with P over 2 zeros and P over 2 ones. So if P was 10, then I would have 5 zeros, 5 ones. And that's clearly in the language because I'm defining it to be. Here's the problem. Well, there are two. One of the problems is, what if P is odd, which it could be, and then dividing by 2 wouldn't make sense. Well, then you say, well, okay, well, let's just put a ceiling on both of these, round up to the nearest integer, and that would be fine. The second problem is one of the conditions of the pumping lemma says that x, y has length at most P, and typically what we want to do is to have x and y be of the same character. We call that uniform, which means that they don't consist of anything other than a single character. And here, because the first P characters can have zeros and ones, so could x and y. So I don't recommend that string, although you could pick it and that would work. It's just that if you pick a string in the language of length at least P, it's not guaranteed to work, okay? A much better string is to be 0 to the P, 1 to the P. And that avoids that problem because all of the first P characters are exactly the same. And we'll see why we want all the characters to be the same in a second. Okay, So how do we actually do this? Well, we need to look at every single possible decomposition of the original string. So let's look at all decompositions of that string W into those three pieces. Well, we know that the first P characters are zeros, because that's how we designed the string. So the condition that X and Y have length at most P together mean that X and Y only have zeros in them, which is the reason why we pick this string over this one. So what we can tell is that X entirely consists of zeros, Y only consists of zeros, and Z is the rest of the string. The way we write this is that X is some number of zeros. I don't know how many of them, but it's some number of them. And note that X itself could be empty potentially. So the way I write this is 0 to the alpha, where alpha is just some number at least 0. Okay, and what we do with Y is 0 to the beta, that's how I typically write it, where beta in this case is at least 1, crucially, because the length of Y is at least 1. And beta is the length of Y, alpha is the length of X. Okay, so what is the rest of the string going to be? Well, if we started off with P zeros right here, and we took away alpha to get X, and beta more to get Y, that means we're going to have P minus alpha minus beta, excuse the gigantic airport apparently right outside my window. Anyway, so we have P minus alpha minus beta zeros left, and all of the ones, crucially, all of the ones are still here. And one thing I could say, although it's not actually necessary, is that alpha plus beta is at most P. And this is just really another way of saying that XY's length is at most P. It's the same thing. We don't actually need this, but it's just something that some students want to see sometimes. Okay, so then now what we need to do as a final step in my magic, my magic tricks here, is to choose one I such that X, Y to the I, Z is not in L. And remember that L is 0 to the n, 1 to the n, where n is at least 0. Okay, so what I want to do here is I want to obtain a string by putting fewer or more copies of Y only, so that I achieve a string that doesn't have some number of zeros than ones and the same number of them. In other words, I want a different number of zeros and ones. So there's an art in doing this. There's no like science, like here is the way that works, but it's just trying to observe what happens. Think about it. If I put more copies of Y in, then that means that the number of zeros in the string goes upward, right? Because the Y part does not contain any ones whatsoever. But the number of ones never changes because the number of Z's that I have in the string remains unchanged. So let's pick I to be 2. I can't pick I equal to 1 because that's the original string. And the original string is in the language. I want something, I should say not in the language. Whoops. Such that this is not in the language. That's what I meant to say. All right. So what is x, y squared z? So squared means 2 in the exponent. Well, what I do here is I just copy and down all of the 3 pieces. So the x part is going to go right here, so 0 to the alpha. We're going to have, what color? Let's do green. We're going to have 2 occurrences of y because that's what I is equal to. That's how many y's I'm putting in. Not a straight line. So I'm going to have 0 to the beta and another 0 to the beta. And then finally, let's do pink for z, which is going to go over here. So 0 to the p minus alpha minus beta, 1 to the p. Okay? Well, there's a lot of 0 segments here. What I do is I just squish them all together. Just add up all the exponents together. Well, what we can see is that the alphas are canceled because I have a plus alpha here and a minus alpha here. One of the betas here and this beta gets canceled again because this is positive, this is negative beta. So I'm left with a single beta left plus the original set of p right here. So when the dust settles, I'm going to have p plus beta zeros, and all of the ones are still there. So the only way that this string right here can be in here is if the two exponents are the same. So this is in L if and only if p plus beta is equal to p, which is the same thing as beta equaling 0, which is impossible. Because the condition says that beta is at least 1, and the only way that it could be in the language is if it's 0, which gets us our contradiction. And then therefore, this string is an example of how this language cannot possibly be regular. So L is not regular as a result. Okay, so that's the general proof strategy that we're going to use here. Okay, so let's move on to another language, which is slightly different, which is going to be, I'm going to call it L2, which is going to be 0 to the I, 1 to the j, such that I is strictly bigger than j. You could make that strictly or equal to. It doesn't actually make a difference in terms of whether it's regular. This one I'm going to show is not regular either. Okay, so how would we actually do this? So what we need to do, as before, is we need to suppose L2 is regular. And then there exists, I'm going to actually shorten this to be a P for L2. Okay, so there's a pumping constant P. It's just a shorthand for the same thing. Okay, so now the important part is, again, picking a string. So let's pick a string W. Again, we got to pick a string that's in the language and has length at least P. Well, I can't pick 0 to the P, 1 to the P here, because the number of zeros is not strictly bigger than the number of ones. In fact, it's the same. So what I'm going to do here is I'm going to pick P plus 1 zeros. It turns out that if I picked P plus 2 or more zeros, this will not be a good string. We'll actually see why that is in a second. Okay, so this string is, so this is in L, and the length of W is certainly bigger than P because the string has like 2P plus 1, so it definitely has enough length. Okay, so then now we need to look at all decompositions again. Look at all decompositions. Well, again, the first P characters are zeros. So we're going to actually have very similar decompositions, just like before. So I'm going to call X to be 0 to the alpha, where alpha is at least 0. Y is going to, again, be 0 to the beta, where beta is at least 1. Remember, is at least 1. And Z is going to be slightly different. It's going to be P plus 1 minus alpha minus beta, because here I started off with P plus 1 zeros, okay? And then I have all of the ones still over there. Okay, so then now, again, we need to choose a value of I such that, now I'll get it right this time, x, y to the I z is not in L2. Remember, it can't be in L2 for us to get a contradiction. If it is in L2, that doesn't help us whatsoever in showing that it's not regular. Okay, well, what can we do here? Well, suppose I put 2 or more copies of y into the string, meaning that the number of zeros goes up, just like before. But for this language, it's slightly different because I have p plus 1 zeros to start with. And if I put more zeros into the string, then this condition is never going to be violated. It's still going to always have more zeros than ones. So we got to actually think about it from the other perspective. We got to take away a copy of y, which we're allowed to do, because as long as I is at least 0, then we're good. So let's actually try to pick I equal to 0, which means that we have 0 occurrences of y. So x, y to the 0, z. Well, any string picked 0 times is going to result in the empty string. So this is just going to be the same thing as xz. Well, again, I'm going to copy down the pieces, just like before. So I'm going to have 0 to the alpha for the x part, and then 0 to the p plus 1 minus alpha minus beta, 1 to the p. Okay, so that's just copying down the multiple pieces. Well, here, just like before, the alphas are going to cancel. The beta is not going to cancel because I don't have the other piece of y there. So when the dust settles, what I'm going to have is 0 to the p plus 1 minus beta, 1 to the p. Okay, well, what can we say here? So this is in L2 if and only if the number of zeros is strictly bigger than the number of ones, which means that p plus 1 minus beta is strictly bigger than p, because p here is the number of ones, and this guy is the number of zeros. Well, if we can subtract p on both sides, which means that 1 minus beta is strictly bigger than 0. And if I add beta on both sides, I get 1 strictly bigger than beta. But that's a contradiction because beta is at least 1. This is saying that beta is strictly less than 1. So this is a contradiction. Okay. And so therefore, what we can conclude is that L2 is not regular. So this was actually a slightly different example where we have to pick the I carefully so that we can actually subtract the number of zeros out, because initially the number of zeros is bigger and the zeros are the beginning of the string. And if I picked any string with p plus 2 or more zeros, then what I would get here is 2 or some bigger number strictly bigger than beta, but that possibly might be that beta is equal to 1. And so beta is allowed to be 1 possibly, and so that's not going to help us whatsoever. Okay, so that's why picking the string is actually important, because it allows you to get really, really close to being not in the language. That's one of my proof strategies for languages like this. If there's some kind of greater than condition or something, what I want to do is I want to pick something that's right on the borderline of not being in the language, and then use the pumping criteria to push it over the edge and get it to be not in the language anymore. So for this one, if I deduct 1 more 0, then it's not in the language anymore. Okay, so it's right on the edge of not being in the language. Okay, so let's do two more examples, which I think are interesting. And I've done them on the channel before, but they're so cool, I like doing them. So I'm going to call this language S, and what is it? Is the set of perfect squares. And what do I mean by this? I mean a string of entirely zeros, so there's no ones or anything, but the number of zeros is always a perfect square. So no occurrences of 0, or 1 occurrence, or 4 occurrences, or 9 occurrences, or 16 or 25. Any perfect square number of zeros is allowed. Okay, so I want to show that this is not regular. Okay, so what do we actually do here? So the first two proofs that we did are actually pretty standard. These are a little bit more, you have to think about it a little bit, which is perfectly fine, but it's not in exactly lining up with the proof strategies that we did before. There's some cleverness that is done here. So again, let's suppose S is regular. And then we now know that there exists a P for S, this language S. Again, P is the pumping constant. So now we got to pick a string that is that's in the language and of length at least P. So the pretty obvious one to pick here is to choose W to be 0 to the P squared. The general technique is whenever there's an N or some variable in the actual language right here, put the pumping constant for that variable. So you see the N here? I just substitute P for N, and usually that works, and in this case it will. Okay, well, we know that every decomposition of this string, every decomposition of W into X, Y, Z will be of the form X is going to be some number of zeros, Y is going to be some number of zeros, and Z is going to be P squared minus alpha minus beta zeros, because there are no ones in the string whatsoever. So actually here, it's not really that important to talk about the decomposition directly in terms of the actual decomposition. What really matters is the length of the string, because the entire string is just all one character. And we're just figuring out whether the length is a perfect square. We don't care about the string itself, we care about the length of the string. So you could do it this way. We're going to do it a little bit more simply. So let's see. Well, we know that the length of, and what you would choose here for the value of I is going to be 2. So very often picking I equal to 2 is a good example, although it wasn't in the last one. It's a good example in general. So let's pick the length of x, y squared z is going to be p squared, which is the original string, plus the length of y. Right? Because the original length was p squared, and I'm adding another copy of y here. Well, what we know is that we know that the length of y is at least 1, no matter what. So actually what I'm going to do is I'm going to move this right here. Oops. And so we know that this is at least as big as p squared plus 1. Okay? But what we're asking here is that can this, so p squared plus the length of y, ever be a perfect square? Okay, it might be, it might not be. So let's see, well, this one right here, the lower bound, because length of y could be exactly 1, it could be. So this length could be achieved, but what we know for sure is that the length p squared with nothing added onto it cannot be achieved. Why? Because the best I can do to get to this is with a +1 right here. I can't do possibly any better than that. So this tells us that the length of this, the string that we got, cannot be equal to this perfect square. Okay? Well, it might conceivably be equal to some other higher perfect square. It's bigger than this one, but it might be equal to some other one. Okay? So, well, what we know, so what can we actually infer about how big the length of y could be? Well, let's actually remember that the length of xy is always at most p, no matter what, because that's one of the conditions. So what can we do with this? Well, we know that the length of x is always, it could be 0, potentially, but so that tells us that the length of y could never be bigger than p itself. So this tells us that this guy is at most p squared plus p, because the x and y together are not bigger than p, so y itself can't be of length bigger than p. Okay, so where is this guy in relation to a perfect square? Well, if we actually think about it, let's look at p plus 1 squared, which is the next perfect square after this one. Okay? Well, if we expand that out, that's p squared plus 2p plus 1. But if we compare these, this one right here, the one that it could be in length, is always strictly less than this one because of this +1 right here. Okay? So this is strictly less than p squared plus 2p plus 1. Why am I even telling you this? Well, let's see. This perfect square and this one right here are consecutive. There are no perfect squares in between. So and it cannot possibly be equal to either of them. The length could not possibly be equal to this one because of this strict inequality, and it can't be equal to this one because of this strict inequality. So it's strictly in between two consecutive perfect squares. Isn't that pretty cool? So that actually tells us immediately that this cannot be a perfect square, which is pretty cool. So that actually tells us that L2, I called it S this time. So S is not regular. Okay, so that was a little bit more tricky because we didn't have to think about the actual string. All we needed to think about was the length. And we needed to think about, well, how can I bound where the length of this resulting string could be? Is it between two consecutive perfect squares? Then that's all we really needed. Well, if it could be bigger than some perfect square and smaller than it with some other decomposition, it might be equal to that perfect square. So that's why picking I equal to 2 was important here. We could pick I equal to 3 and put down in the comments whether or not that works. I equal to 3, you should try. I equal to 4 will not work necessarily. There may be a way to work it, but not in this direct way. Okay, so let's do one more language. So I'm going to call this this language primes. So this is going to be 0 to the n, where n is a prime number. Okay, and what I want to do is I want to show that this is not regular either. So how would I actually show this? Well, again, what we need to do is to suppose that this language primes is in fact regular, and there exists for that reason a pumping constant p for this language primes. Okay, so what can we actually do with this? Well, again, we gotta pick a string that's in the language of length at least p. So a lot of what my students do a lot is they choose w to be equal to 0 to the p, because p obviously stands is a prime number because p stands for prime. It's the first letter. The problem with that is that p itself might not be a prime number. So we can't pick this string, but the great thing is that there always is a prime bigger than p. And how do I know for sure? Because there are infinitely many primes for a number of reasons. And I'm sure you can find proofs of why there are infinitely many primes, but there are infinitely many primes. So what we can do is just pick any prime that's bigger than this number p. So what I'm going to do here is I'm going to pick 0 to the r, where r is a prime at least p. But I'm going to actually make a slight adjustment. And it turns out that it doesn't really matter because, again, there are infinitely many primes. I'm going to pick p plus 2 here. And there's a very good reason for this. So you might actually be able to guess based on this observation. Well, we gotta pump this string. We gotta insert additional copies of y such that we hopefully leave the primes language. We get a string that is not prime in length. Well, if I give you a number and I assert to you that it is prime and you don't believe me, how would you convince me it's not prime? You would give me 2 factors of the number that and it's not 1 or the number itself. It's got to be 2 numbers that multiply together to equal r in this case, and they're both at least 2. Okay, so like for example, if I looked at the number 15, then it's equal to 3 times 5. So 15 is the product of 2 numbers where both of the 2 numbers are at least 2. And that would be a way to show that the number is not prime. So you might actually be able to guess why I put a plus 2 here. Okay, it's mainly because of that reason. Okay, so what would we actually do here? Well, the thing is, I don't know necessarily which value of I to pick. Before, it was pretty clear what to do, because as long as it didn't ever get close to this upper bound right here, this next perfect square, or in the other cases, as long as the criteria was not met, then that was fine. It's not really clear here because it might be possible that wherever this prime is, there's a prime really, really close to it. And so it might be that if we pumped, we get to that particular next prime. So what I want to show is that you can actually avoid that at some point. But the thing is, I don't know necessarily which value of I to pick. So we're actually going to do something that's actually really clever, which is we're not going to pick the value of I at the start. We're going to wait until the end and then pick the value of I. So we'll handle it in its full generality and then put the value of I in at the end so that it works, which is really, really nice. So again, because this language only has zeros in it, we only care about the length of the string. We don't care about the string itself. So what I'm going to do here is I'm going to look at x, y to the I, z, and I'm going to look at the length of that string. And I don't know what value of I to pick. And I want to pick a value of I eventually so that this right here, this length is composite. It's a product of 2 numbers that are both at least 2. Well, we can actually break this, because we're only caring about the length, I can actually split the string up. And the way I'm going to do that here is the following. This length right here is equal to the length of xz plus the length of y to the I. So I'm just extracting this piece right here and pulling it away. I can do that because I'm only caring about the lengths. And I didn't add any i's or y's or x's or z's. I didn't change anything. Another thing I'm going to do is I'm going to have x, z's, so that's unchanged, but I'm going to have I times the length of y right here. And I can do this because y to the I is just y concatenated with itself I times. So if I only care about the lengths, is I copies of the length of y, because it's just copying y over and over. Okay, well, what can we say about this here? Well, what we can say is we want to show that this is the product of two numbers, both at least 2. Well, how can we actually do that? Well, what we can say is we know that so let's actually put a little bubble over here. So what we know is that the length of x, y, and z together, which is the original string, is at least p plus 2. Right? Because that's what we picked the length of the string originally to be. It's the length of the pumping constant plus 2. So that's the plus 2 here. But we know that xy right here is of length at most p. Right? We know it's of length at most p. It's within the first p characters. So that actually tells us something interesting, in that the length of z by itself is at least 2. Because the length of xy can at worst take p characters, which leaves z characters for, which leaves 2 at least characters for z. So then what can we say about this? This is at least 2, because z itself is of length at least 2, and x might add more, might not. So if there is some way that we can have xz times something, such that what we can guarantee for here is that this is at least 2, then we're done, because this one is at least 2. So if there's some way I can put something in here that's equivalent to this one, and we can guarantee it's at least 2, then we're done. But what can we do here? What we can do is notice that the length of y y itself is of length at least 1. And how do I get something from 1 to 2? The easiest way is to add 1 to it. So what I can put in here is 1 plus the length of y. And that would get us exactly what we want. But how can I show that this is equivalent to the original? Well, if we expand this product out, we'll get xz's length, because it's just multiplied by 1, plus xz's length times the length of y. So the correct value of I to pick is going to be the length of xz. Isn't that weird? So if I pick this value of I, then I will get something that is composite, is something two numbers that are at least 2 together, multiplied together, to get the original prime number, supposedly, but it's not prime because those two numbers are at least 2, which means that the string is not in the language anymore. Okay? And you may think, well, oh no, that's illegal. You gotta pick I to be 2, you gotta pick I to be 3, or some number. I actually don't. Revisit the pumping lemma proof. It turns out that you don't actually need the value of I to be fixed in every single decomposition. It could vary depending on the decomposition. And once you notice that, then I'm allowed to do things like this, which shows us that we can get a string that is not in the primes language anymore. So what we can gather from all this is that primes is not regular. Okay, I know it was a really long video, but we were able to accomplish a lot. We went over 4 different pumping lemma style proofs. We started with a simple example, 0 to the n, 1 to the n. Then we did 0 to the I, 1 to the j, where there are more zeros than ones. Then we did perfect squares. Then we did primes. And each one of them used a slightly different technique, but the general principle is the same. You suppose that the language is regular. Then you know that there's a pumping constant for that language. You pick one string in the language of length at least p. Then you look at every single decomposition, not just one or a few, every decomposition, and then you pick a single value of I such that x, y to the I, z is not in the language that you want, which contradicts the fact that the language was regular. Because if it were regular, then it would be in the language for every choice of I, and we chose one that it wasn't in the language. So I hope that was interesting. Leave in the comments any additional languages you think are interesting to show that they're not regular, or you have any other proof strategies. I'm happy to hear everything that you guys suggest. As always, please like and subscribe to the channel. It really helps us out. There are many other links in the description down below if you want to contribute additionally, such as our Patreon or our Discord server, or you can just make a donation and the donation will appear on stream. So if you want to donate during a stream and have it seen, you can do so then. And as always, I'll see you next time. Thanks.